Alright, that should be me. I think everything is coming up. Alright, so today I wanted to build, we'll really do chapter 12, and this is where we create a command line program. So this will be sort of the last of a series of me going through this book. We've pretty much hit the halfway point, and I wanted to slow down my tempo of reading this book because every stream for the past couple weeks has been me reading from this book, and so I want to start to pursue other things while also spending some time reading. So maybe I'll alternate. Maybe one stream is devoted to my own personal project, and another stream is devoted to reading more from this book. And so the tempo will slack after this stream, but we're here to build the command line program. So I'll start with reading aloud this introduction, and then we'll move to the rest of the 6 sections. So this chapter is a recap of the many skills you've learned so far, and an exploration of a few more standard library features. We'll build a command line tool that interacts with file and command line input and output to practice some of the Rust concepts you now have under your belt. Rust speed, safety, single binary output, and cross-platform support make it an ideal language for creating command line tools. So for our project, we'll make our own version of the classic command line tool, grep. In the simplest use case, grep searches a specified file for a specified string. To do so, grep takes as its argument a file name and a string. Then it reads the file, finds lines in that file that contain the string argument, and prints those lines. Along the way, we'll show how to make our command line tool use features of the terminal that many command line tools use. We'll read the value of an environment variable to allow the user to configure the behavior of our tool. We'll also print error messages to the standard error console stream instead of standard output. So for example, the user can redirect successful output to a file while still seeing error messages on screen. One Rust community member, Andrew Gallant, has already created a fully featured, very fast version of grep called ripgrep. By comparison, our version of grep will be fairly simple, but this chapter will give you some of the background knowledge you need to understand a real-world project such as ripgrep. And our grep project will combine a number of concepts you've learned so far. Organizing code from chapter 7, using vectors and strings, chapter 8, handling errors from chapter 9, using traits and lifetimes where appropriate from chapter 10, and writing tests, chapter 11. Did I go over writing automated tests? I don't think I did. I think I accidentally skipped that chapter. Oh, we'll just do number chat. Oh, I guess we'll just skip it. Alright. Yeah, we'll skip chapter 11 for now. We'll just go straight to chapter 12. Because in the real world, you know, we always skip writing automated tests. Yeah, we go straight to the project. Alright, we'll learn what we need on the fly. Alright. Okay. Alright, so now we're going to create a new project. So I'm going to open up my workspace. It was Rust Lane book. Just open this in terminal. What was it? Cargo new mini grep. Alright. cd mini grep code dot, and then we'll just get rid of these. Alright. So now we have everything that we need. We'll open up our integrated terminal. And we'll open up the source file. So if we cargo run search string example file. Alright, so what are we gonna do? The first task is to make a mini-grep accept its two command line arguments, the file name and a string to search for. That is, we want to be able to run our program with cargo run, a string to search for, and a path to a file to search in, like so. Where it says cargo run, search string, example, file name.txt. And right now we can't process arguments. So we'll implement this capability right now. So we need to be able to read the values of command line arguments, and that capability will come from environment variables or arguments. So this function returns an iterator, the command line arguments that were given to mini-grep. You only need to know two details about iterators. Iterators produce a series of values, and we can call the collect method on an iterator to turn it into a collection, such as a vector containing all the elements the iterator produces. Alright. So let's just copy this and paste it here, and then bam. Let's see if this works. So what are we doing? I'm gonna do cargo run, see what happens. Alright, so it seems that when we do cargo run without any arguments, it has always a default, which I suppose is, so this must be the location of the binary that, what is this? Is it the binary? I think this is the actual binary. And so the first argument automatically passed in to the program by just calling cargo run, like in this example, is the location of the binary relative to the root. And if we add arguments, it'll pretty much add them and then you can iterate over them, but in this case we just collected the iterator and then we printed it. And so if we did something else with another word that says hello world separated by white space, we have two different arguments, right, coming in. But if we were to just put them together without separated by white space, then we get just a single argument. So that's what we got. Alright, so we pretty much made a vector of strings for the arguments that are passing in. We called environment args to get those in, to get the iterator of those arguments, and then we collected them into a vector of strings. And then we just printed those arguments out. And the way we were able to use env directly like this because we brought it as a namespace, right? So we can now use standard env directly here. All right. The reason we didn't just bring in standard env args, just the args function, is because of precedent, right? This is the idiomatic way to do it in Rust. And it allows you to be less ambiguous. All right. Uh-oh. Note that standard environment args will panic if any argument contains invalid Unicode. If your program needs to accept arguments containing invalid Unicode, use standard environments args OS instead. That function returns an iterator that produces OS string values instead of string values. We've chosen to use args here for simplicity because OS string values differ per platform and are more complex to work with than string values. Oh man, string values are already sort of hard. All right, can't imagine working with OS strings. On the first line of main, we call and we immediately use collect, and then we create a vector out of it. So it seems that collect is one function that we do need to annotate because Rust is not really able to infer what we mean when we use it, because we could have collected this into any number of things, but we wanted to collect it into a vector of strings. So then we print it. All right. Yeah, so it's the binary. So the first argument here is the binary. So that way, the program can use the name by which they were invoked in their execution. So that's why they passed it in. Okay. All right, so now we're going to let the query be a reference to the second argument, which is the first relevant one, and file name be the reference to the third argument here. And they'll be query and file name respectively. So we'll just copy this. We'll put it here, and then we'll do that. So we don't do any error checking. So we only passed in one argument, or one relevant argument. I'm just going to say argument for now. Well, from now on. And that argument, there was another one for file name to actually reference, and here it's saying the length is 2, but the index is 2. So file name is trying to access the third element in the vector strings, but there are only 2: the name of the binary and hello world that we passed in. So we're going to separate those out. And now we get what we're looking for, where it says searching for the query, and we're searching for that in the file called world. So I can say that we're trying to find something world.txt, for example. Oh. All right. Let's see, actually. Yeah, everything looks pretty good. All right. All right. All right, so the program is working. We are able to save the 2 arguments that we care about. And we're just ignoring the error, in which case the program just panics. All right. So now we'll add functionality to read the file that is specified in the file name command line argument. First, we need a sample file to test with. The best kind of file to use to make sure mini grep is working is one with a small amount of text over multiple lines with some repeated words. So let's copy this into here. We'll call it poem.txt as they recommend. And now we're going to edit the main. We'll leave those debug statements there. So we repeated that. We don't have fs. This is the file system. library that we're going to use and add it to our namespace. So what are we doing? We're letting the contents be read to string of the file name here, the second argument, and we're going to expect, so this is if something goes bad, then we just say something went wrong with reading the file, and then we panic. So if I do this with cargo run hello world.txt, it's going to panic. And it panics at line 14, which makes sense because this is where we're trying to read from the file name, which doesn't exist. But if I instead try to read from poem, it'll take that content and then it'll print it out here along with text. All right. Right, expect takes result string, sees if it's okay. Is result the one that comes with okay and error? I think it does. And so if it's okay, then it'll just unwrap string and then put it into contents, right? So pretty much expect attempts to unwrap whatever is returned here. So this result attempts to unwrap that and plug it into contents. But if it can't, if result happens to be an error, then we print something went wrong. Yeah, so this is exactly what we got. Alright, so the code read and then prints the contents of the file, but code has a few flaws. The main function has multiple responsibility. Generally, functions are clearer and easier to maintain if each function is responsible for only one idea. The other problem is that we're not handling errors as well as we could. The program is still small, so these flaws are not a big problem, but as the program grows, it will be harder to fix them cleanly. It's good practice to begin refactoring early on when developing a program because it's much easier to refactor smaller amounts of code. We'll do that next. So yes, refactoring. Oh, look how big that is. That's why you love refactoring. All right. So to improve our program, we'll fix 4 problems that have to do with the program structure and how it's handling potential errors. First, our main function now performs 2 tasks. It parses arguments and reads files. For such a small function, that is not a major problem. However, if we continue to grow our program inside main, the number of separate tasks that main function handles will increase. As the function gains responsibility, it becomes more difficult to reason about, harder to test, and harder to change without breaking one of its parts. It's best to separate functionality so each function is responsible for one task. This issue also ties into the second problem. Although query and file name are configuration variables to our program, variables like contents are used to perform the program's logic. The longer main becomes, the more variables we'll need to bring into scope. The more variables we have in scope, the harder it will be to keep track of the purpose of each. It's best to group the configuration variables into one structure to make their purpose clear. Third problem is that we've just used expect to print an error message when reading the file fails. But the error message just prints something went wrong reading the file. Reading a file can fail in a number of ways. For example, the file could be missing, or we might not have permission to open it. Right now, regardless of the situation, we'd print the something went wrong reading the file error message, which wouldn't give the user any information. Fourth, we use expect repeatedly to handle different errors, and if the user runs our program without specifying enough arguments, they'll get an index out of bound errors from Rust that doesn't clearly explain the problem. It would be best if all the error handling code were in one place so future maintainers had only one place to consult in the code if the error handling logic needed to change. Having all the error handling code in one place will also ensure that we're printing messages that will be meaningful to our end users. Now we'll address them. Alright, so we separate concerns now. The organizational problem of allocating responsibility for multiple tasks to the main function is common to many binary projects. As a result, the Rust community has developed a process to use as a guideline for splitting the separate concerns of a binary program when main starts getting large. The process has the following steps. Split your program into a main source file and a lib source file and move your program's logic to lib. As long as your command line parsing logic is small, it can remain in main. When the command line parsing logic starts getting complicated, extract it from main and move it to lib. The responsibilities that remain in the main function after this process should be limited to the following. Calling the command line parsing logic with the argument values, setting up any other configuration, calling a run function in lib, and handling the error if run returns an error. This pattern is about separating concern. Main handles running the program and lib handles all the logic of the task at hand. Because you can't test the main function directly, this structure lets you test all of your program's logic by moving it into functions in lib. The only code that remains in main will be small enough to verify its correctness by reading it. Let's rework our program by following this process. So now we're going to extract the argument parser, but first, I'm going to get some water. Alright, I'm back. So first we'll extract the functionality for parsing arguments into a function that main will call to prepare for moving the command line parsing logic to source lib. So first let's just create the lib.rs. Alright, so first we just get the arguments into a vector and then we parse that vector and then we assign a tuple of query and file name to whatever is returned from this. And the parse config is going to be this, which is very, very simple. In fact, we'll test it in main first. So we're going to let query and file name equal parse config of a reference to args. And this should work what we did before. Alright. So we now have a function that parsed the config. We still had to collect the args here. It's still in main, but we're able to move the logic of parsing the config arguments outside of main, and that's really the key. And it wasn't much logic, but we parsed it. We were able to remove it regardless. And the next step, as I'm sure it's going to tell us, is to move parse config to lib and then add it to our namespace using the keyword use. Right, so it's only after we get the vector and after passing it through parse config that we get query and file name instead of referencing the arguments directly. So the parse config function then holds the logic that determines which argument goes in which variable and passes the values back to main. We still create the query and file name variables in main, but main no longer has the responsibility of determining how the command line arguments and variables respond. This rework may seem like overkill for a small program, but we're refactoring in small incremental steps. After making this change, run the program again to verify that the argument parsing still works. It's good to check your progress often. Say that again. Alright. You can take another small step to improve the parse config function further. At the moment, we're returning a tuple, but then we immediately break that tuple into individual parts again. This is a sign that perhaps we don't have the right abstraction yet. Another indicator that shows there's room for improvement is the config part of parse config, which implies that the two values we return are related and are both part of one configuration value. Alright. We're not currently conveying this meaning in the structure of the data other than by grouping the two values into a tuple. We could put the two values into one struct and give each of the struct fields a meaningful name. Doing so will make it easier for future maintainers of this code to understand how the different values relate to each other and what their purpose is. So using primitive values when a complex type would be more appropriate is an anti-pattern known as primitive obsession, and something you want to avoid. So now we're going to have a config struct. So we'll have struct config, and we'll have two things here of query and file name. And these will both be of type string. Alright. And then after that, so we're going to take the args and clone it. Alright, so instead of referencing the args that are passed in as an argument in the parse config function directly, we're going to clone it into the config struct, because the config struct does not hold a reference to a string, it just holds a string, and so you can't really assign ownership of a single element of an array to some other entity, because then it would sort of break the original array, which might have other entities or other elements that it worries about. So we're going to clone. Alright, so it's going to now return a config, and we're going to clone this and clone this, and then we're going to return config of query and file name, and then we're going to let config equal this here. And then we'll, I guess, reference config dot here. Config dot. And config dot. That should fix everything. Alright, So we've added a struct named config defined to have fields named query and file name here. The signature of parse config now indicates that it returns config value here. In the body of parse config, where we used to return string slices that reference string values in args, we now define config to contain owned string values. It owns it because we called clone, and here is where it returns it. The args variable in main is the owner of the argument values and is only letting the parse config function borrow them, which means we'd violate Rust's borrowing rules if config tries to take ownership of the values in args. Right, because you're passing a reference to an array of strings, then you can't, then that means that this function is borrowing, it's not taking ownership. We could manage the string data in a number of different ways, but the easiest, though somewhat inefficient route is to call the clone method on the values. This will make a full copy of the data for the config instance to own, which takes more time and memory than storing a reference to the string data. However, cloning the data also makes our code very straightforward because we don't have to manage the lifetimes of the references. In this circumstance, giving up a little performance to gain simplicity is a worthwhile trade-off. So we'll talk about the trade-offs. There's a tendency among many Rustaceans to avoid using clone to fix ownership problems because of its runtime cost. Chapter 13, you'll learn how to use more efficient methods in this type of situation. But for now, it's okay to copy a few strings to continue making progress because you'll make these copies only once and your file name and query string are very small. It's better to have a working program that's a bit inefficient than to try to hyper-optimize code on your first pass. As you become more experienced with Rust, it'll be easier to start with the most efficient code, but for now, it's perfectly acceptable to call clone. We've updated main so it places the instance of config returned by parse config into a variable named config. Here when we were calling it. Doing so helped us to see that query and file name values were related and that relationship should be conveyed in our code. We then added a config struct to name the related purpose of query and file name, and to be able to return the values names as struct fields names from the parse config function. So now that the purpose of the parse config function is to create a config instance, we can change parse config from a plain function to a function named new that is associated with the config struct. Making this change will make the code more idiomatic. That is, more Rust-like. We can create instances of types in the standard library such as string by calling string new. Similarly, by changing parse config into a new function associated with config, we'll be able to create instances of config by calling config new. This is how we do so. So this is going to be the new way of calling config, but for now we'll just implement config. So I'll put it right after the struct definition. So the implementation of config is going to be new. And it's going to take args as it did before. This is pretty much the identical function as parse config, right? But instead of parse config, we're going to do config new. And then we'll get rid of parse config. And then we'll call the same thing. And it works. So now we're going to fix the error handling. Recall that attempting to access the values in the args vector at index 1 or index 2 will cause the program to panic if the vector contains fewer than 3 items. Try running the program without any arguments. It'll look like this. We tried that already. The line index out of bounds, the length is 1, but the index is 1 is an error message intended for programmers. It won't help our end users understand what happened and what they should do instead. Let's fix that now. So in the new function, we're going to check if args, the length of the arguments collection is less than 3. And if it's not, or if it is, then we're going to panic, not enough arguments. So let's add that in right now. So you see now the logic for parsing through the arguments has become slightly more complicated, and we're grateful that we abstracted it out of main. Now if we did this, thread main panicked at not enough arguments. So now the error message is clear. And it should work with the original, which it does. Cool. Yep, and so when we run it, we get the error message that we just saw, and now we say the output is better. The problem is that we also have extraneous information we don't want to give to our users. Perhaps using the technique we used in listing 910 isn't the best to use here. A call to panic is more appropriate for a programming problem than a usage problem. Instead, we can use the other technique you learned about, which is returning a result that indicates whether success or an error. So we'll return a result of config. Is that how you do it? Reference to stir. So string slice. So result will either have the config, which will be an OK struct, or it'll have the error string. We need to be able to parse through config here. Sorry, we need to be able to parse through the config new here, because right now we return a result, and you can't directly unwrap it without calling the unwrap function, right? But we don't do that here. We just try to reference the data within config immediately without unwrapping it first. So instead of calling panic, when the user doesn't pass enough arguments, we now return an error value, and we've wrapped the config return value in an OK. These changes make the function conform to its new type signature. Returning an error value from config new allows the main function to handle the result value returned from the new function and exit the process more cleanly in the error case. So now we're going to call config new, and we're going to use the unwrap or else. So we're going to attempt to unwrap the result, or else we take that error and we print problem parsing arguments and the error message, and then we exit. So we first need to use standard process to be able to exit. And we'll let config attempt to unwrap or else. And it should work if we have the poem, and it should not here. It says problem parsing arguments, not enough arguments. See, that looks much cleaner than what it was before. I mean, what is all this, right? So there you go. So in this listing, we've used a method we haven't covered in detail yet, unwrap or else, which is defined on result of TE by the standard library. Using unwrap or else allows us to define some custom non-panic error handling. If the result is an OK value, then this method's behavior is similar to unwrap. It returns the inner value OK is wrapping. However, if the value is an error value, this method calls the code in the closure, which is an anonymous function we define and pass as an argument to unwrap or else. So this is the anonymous function, and this is the argument that we pass into it. For now, you just need to know that unwrap or else will pass the inner value of the error. So it'll still unwrap the error object and give us the string slice. And then we'll take that string slice here as the argument into this closure, and then we'll just print it out and then exit from the process. Yeah, so we'll pass the inner value of the error, which in this case is static string not enough arguments, to our closure in the argument error that appears between the vertical pipes. The code in the closure can then use the error value when it runs. We've added a new used line to bring process from the standard library into scope. The code in the closure that will be run in the error case is only 2 lines. We print the error value and then call process exit. The exit function will stop the program immediately and return the number that was passed as the exit status code. This is similar to the panic-based handling we used, but we no longer get all the extra output. So now we're going to extract the logic from main. Now that we've finished refactoring the configuration parsing, let's turn to the program's logic. As we stated before, we'll extract a function named run that will hold all the logic currently in the main function that is not involved with setting up configuration or handling errors. When we're done, main will be concise and easy to verify by inspection, and we'll be able to write tests for all the other logic. So here is the extracted run function. For now, we're just making a small incremental improvement of extracting the function. We're still defining the function in the main source file. So I'll just take this, extract it here, and I'll pretty much run it here. And it doesn't even take a reference to a config as its argument. And this is ignored. So the run function now contains all the remaining logic from main, starting from reading the file. The run function takes the config instance as an argument. So I believe ownership is passed from config to run. I'm gonna test that out. Can I say let x equal config dot file name? No, because it was moved here. Yeah, so run has taken ownership of config. That's what I figured. Alright, so now we're going to return errors from the run function. The remaining program logic separated into the run function. We can improve the error handling as we did with config new in listing 12.9. Instead of allowing the program to panic by calling expect, the run function will return a result TE when something goes wrong. This will let us further consolidate into main the logics around handling errors in a user-friendly way. The following listing shows the changes we need to make to the signature and body of run. So now we're going to use some standard library feature called error for whatever reason. And it's going to return, so run is going to return a result of, I guess, a singleton and box of dynamic error if there is an error. So we encountered the question mark before, and it was sort of shorthand for returning stuff and adding basic result wrapping instead of expect. Forget what the question mark specifically did, to be honest. So we've made three significant changes here. First, we changed the return type of the run function to result of either the unit type or box dyn error. This function previously returned the unit type, and we keep that as the value returned in the OK case. For the error type, we used the trade object box dynamic error, and we've brought standard error into scope with the use statement at the top. We'll cover trade objects in chapter 17. For now, just know that box dyn error means the function will return a type that implements the error trait, but we don't have to specify what particular type the return value will be. This means the function will return a type that implements the error trait. We don't actually have to specify what particular type the return value will be. This gives us flexibility to return error values that may be of different types in different error cases. The dyn keyword is short for dynamic. So before, with the error, when we did the config, sorry, it's over here. We specified that the error was going to be of a type of a string slice, but now it could be any type really. So let me check on the stream. I got a second playback, cool. Anyway. Alright, so what are we trying to do? Where did I leave off? Alright, so this gives us the flexibility to return error values that may be of different types in different error cases. So maybe we'll return string slice in one case or some sort of other object in another case as the type of the error. Because before we were saying that the type of the error was a reference to string. And this reference to string is simply wrapped by an error object. But the type is still just a string slice. But here it could be anything. So weird. Alright, so second, we removed the call to expect in favor of the question mark operator, as we talked about in chapter 9. Rather than panic on an error, question mark will return the error value from the current function for the caller to handle. Okay, so that's why we want the dynamic, right? Because I suppose if we used question mark in multiple different function calls, they each may return a different error depending on their functionality, right? And because of that, if we were to get an error from this with the question mark, it'll automatically return an error and skip over executing everything else. Because of that, we could have any number of different kinds of errors, which implies that we need a dynamic error sort of type. Third, the run function now returns an OK value in this exact case, and this is only after we finish doing everything. We've declared the run function success type as the unit type in the signature, which means we need to wrap the unit type value in the OK value. This OK syntax might look a bit strange at first, but using the unit type like this is the idiomatic way to indicate that we're calling run for its side effects only. It doesn't return a value we need. So it's pretty much a dummy return type. Really, it's useful only as part of a result type, which is only useful for its error handling. That's why we need the dummy OK. So it's gonna, okay, let's see what our warning will be if we get the warning as well. Yes. So run config has a warning because we didn't handle the error function. Or we didn't do any error handling. So Rust tells us that our code ignored the result value, and the result value might indicate that an error occurred, but we're not checking to see whether or not there was an error. And the compiler reminds us that we probably meant to have some error handling code here. Let's rectify that problem now. We'll check for errors and handle them using a technique similar to one we used with config new, but with a slight difference. So we're doing an if let. So pretty much if we can get an error out of run config, then we print what that error is and we exit. Let's put that here. Alright, we use if let rather than unwrap or else to check whether run returns an error value and called process exit of 1 if it does. This is because we don't actually care about what's being unwrapped from okay if it did turn out okay. So the run function doesn't return a value that we want to unwrap in the same way that config new returns the config instance. Because run returns a unit type in the success case, we only care about detecting an error. So we don't need an unwrap or else to return the unwrap value because it would only be the unit type. The bodies of the if, let, and the unwrap or else functions are the same in both cases. We print the error and exit. So now we're going to split the code into a library crate. So it's looking good so far. Now we'll split the source main file and put some code into the source lib file so we can test it and have a main file with fewer responsibilities. Let's move all the code that isn't in the main function from main to lib. The run, used, config, and config new. So they should have the signatures seen here in the lib. And we'll do that over here. And we're going to need to use this lib. I suppose we would have to use minigrep. Yeah, use minigrep config. Oh, we need to make it all pub. 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 Is it pub in? No. Pub. And pub. And then we're going to use minigrep config. Oh shit. Whoops. So that way we can call config directly. And this, I don't know why we can't call run directly. We'll be able to call new, yes, because we can call new config directly here. Is this minigrep run? I believe so. Yeah, so here. So we had to use minigrep config line to bring the config type from the library crate into the binary crate scope. And we prefixed the run function with our crate name. Because I suppose minigrep is just automatically used in the main source file. Now all the functionality should be connected and should work. And if we run, it should work. So I'm gonna do that right now. And it works. And we don't have any sort of warning. Alright. So almost all of our work will be done in the lib source file from here on out. So now we'll write some tests. Here we go. So now that we've extracted the logic into source lib and left the argument collecting and error handling in source main, it's much easier to write tests for the core functionality of our code. We can call functions directly with various arguments and check return values without having to call our binary from the command line. So feel free to write some tests for the functionality and config new and run functions on your own. This section will add the searching logic to the mini-grep program by using the test strip. So we're gonna skip this. So we'll add the searching logic to the mini-grep program by using the test-driven development process. This software development technique follows these steps. Write a test that fails and run it to make sure it fails for the reason you expect. Write or modify just enough code to make the new test pass. Refactor the code you just added or changed to make sure the tests continue to pass. Repeat from step 1. This process is just one of many ways to write software, but TDD can help drive code design as well. Writing the test before you write the code that makes the test pass helps to maintain high test coverage throughout the process. We'll test drive the implementation of the functionality that will actually do the searching for the query string in the file contents and produce a list of lines that match the query. We'll add this functionality in a function called search. Because we don't need them anymore, let's remove the print line statements from source lib and source main that we used to check the program's behavior. Then in the lib source, we'll add a test module that we... Alright. So this looks extremely different than what I've previously encountered in Rust. So it might be wise to go visit writing automated tests first and then come back to it at a later time. Let's check out this. Yeah, you see we continue to make new tests and feel like we could figure it out if we'd like to, but I think it would be wise to create or go back to chapter 11, which we unfortunately skipped out of my oversight, and return to the second half of chapter 12. I think that would be a fairly good idea, especially considering how long this is. Alright, so we'll do that. We'll do the second half of this project after having read through chapter 11. So with that, I think I'm going to be done. I am sort of tired. And so with that, I suppose I will bid adieu. And strange that we had 2 playbacks and the average watch time was 9 minutes. I don't even see any mark of that here. Oh well. Anyway, I'm gonna get off the stream now, and I'll see y'all later. Thanks for watching. Goodbye.